I don't know. Wait, shouldn't this be lecture 21, not 22? The last one was 20.
You're right.
Yeah, Kevin!
Let's say the midterm was lecture 20.
No,
Last time was 21?
At least that's what it's labeled as.
Let's see.
Was labeled incorrectly.
I mean, no.
You know what? I think I'm right because I'm always right. Okay.
Well, doesn't matter.
I'll take a look at it. I'll take a look at it tonight and make sure numbers match up. All right, cool. Let's get started. Welcome to Data 8, Lecture 22. Is the lecture after the midterm. I can see the class attendance reflects that, but that's okay. So I have some announcements to make. So if you did not know or if you forgot, homework 5 is due tonight. Last time I checked, there were a good number of people who did not submit homework 5. So if you did not submit homework 5 yet, please make sure to have it in tonight because it's due. We've released a midterm feedback survey. So we'd like to, at this point in the class, we're halfway done, woohoo. And we'd like to get your feedback on things, how you think the class is going. So if you think it's going well, we want to know. If you think things need changing, then let us know, and we can try to adjust and make the class better for you. Okay. The way we've done it is the survey is anonymous, but if 90% of the class fills it out, you guys get an extra credit point on your midterm. Okay. So the midterm grading is finished. However, we're holding back on releasing the results until after the survey results come in. Okay. So the survey is due tomorrow at 5 p.m. and the midterm grades will be released after that. If like we get 90% of people fill it out tonight, then we'll just release it tonight. So it's kind of like whenever we get the amount of responses on the survey, that's the time we'll release the midterm, or just tomorrow at 5 p.m. Cool. Project 2 has been released, is on the website, and labs today and tomorrow will be devoted to working on Project 2, getting started on that with your partner. It is to me a very interesting project because we're talking about the death penalty and whether or not the death penalty was a good policy. Finally, there is tutoring this week, as usual. I think as of right now, we have a lot of spots. So if you want review of last week's material or this week's material going over the midterm or any of that stuff, sign up for this week's tutoring. There's plenty of spots available. Cool. So let me show you the midterm distribution. So good job, everyone. So it looks like the midterm was out of 50 points. It looks like a lot of people got like 40 in the 40 to 50 range, which is excellent. Really great job. The median score was a 44, and the mean score was a 42.6. Standard deviation is 5.75. So you might not know what those terms mean. We're going to go over it in class soon. You might, but you've probably seen it in other places. So these are the statistics for the midterm. This class is not graded on a curve. Okay, so basically what we're going to do is we're just going to take your midterm score and leave it as it is. We're not going to adjust points. We're not going to ding you down. We're not going to bump people up. It's just whatever score you got on the midterm is the grade you got on the midterm. Yeah.
At the end, do you curve the class, or is it just like if we get 90% enough, that's an A?
So at the end, do we curve the class? As of right now, we're thinking probably not. Just because people seem to be doing well, seems to be no need to curve. So we might just leave it as it is. Sorry?
Do you curve it down or no?
No, we won't curve it down. So basically, we looked at this and we were like, did we make the midterm too easy? And my staff and I sat down, looked at the midterm, looked at you guys' scores, looked at how you guys did on like the different questions we thought would be tricky or more difficult. All in all, we felt like the midterm was on the easier side. Like we didn't include as many like really hard questions as we could have. However, we did feel like on the question that you guys did answer, you guys really showed like your knowledge of the material and did overall, like, we were just like, okay, these people know, for the most part, know what they're talking about. So we're pretty okay with the scores that they came out here. You guys just happen to do really well. It's a great job. All right, so let's go on to the topic for today. How many of you guys have heard of Deflategate? Any takers? Oh, okay. About like 10 of you. Excellent. So Deflategate was a big scandal in the American NFL. And the story is, in 2015, the Patriots and the Colts were playing each other in, I believe, the NFL semifinals, so like one round before the final round. So they were playing each other. And in the second quarter, so American football is in 4 quarters. In the second quarter, one of the Colts intercepted Patriots football. Okay, so each team has their own footballs, and they're responsible for maintaining the pressures on each football. So the Patriots threw the football. A Colts player happened to catch it, and he felt the football, and he was like, this football feels kind of flat. And the reason why you want to make sure your footballs are at the right pressure is because it tends to be the case that flatter footballs are easier to catch. Right? So he was like, this seems really fishy. Maybe they're making their balls flatter than they should be. So he took it to the officials, and the officials were like, okay, this ball does seem flat. And so during the halftime, they investigated like a bunch of footballs and tried to take the pressures of a bunch of them to try to see what exactly was going on. So I believe the pressure that the NFL like requires on its footballs is somewhere between like 12.5 to 13.5 psi. And the question in this case was, did the Patriots actually deflate their footballs more than the Colts did? And the term Deflategate comes from a spinoff of the political term like Watergate. So if you're familiar with American politics, a while back, there was a really big scandal where basically a president tried to spy on other people running against him, and it was called the Watergate scandal, and people clearly felt the same way, because here's Tom Brady exiting the stadium, and then here's this guy, cheaters exit here. It was just a big deal. He got fined like $1 million, I think, which is a lot of dollars. And about 1.5 years later, he's like, I've just moved on, man. So let's take a look at the footballs and try to see if we can decide for ourselves whether or not the footballs were deflated. Okay. So one interesting thing about all this stuff happening is that the NFL hired an external law firm to kind of look at the data, to try to investigate like what the players said to each other, all of that stuff, to try to investigate whether or not these footballs were actually deflated, and whether or not, more importantly, whether the Patriots were actually cheating in this football game. So they investigated all of that stuff, and they made their data available. We're going to take a look at their data. Okay. All right, close that. So here's a nifty thing that I'm trying out for this lecture. So if you go to our website, you can actually, and you have your laptop and you'd like to follow along, what I've done is I have pre-uploaded squished together. I pre-uploaded the lecture notebook. Okay, so if you go to Monday, you'll see that the demo link is already online. If you click that link, you'll get this blank notebook, which is the exact same notebook as I have here. So if you want to follow along, go ahead. I don't expect you to follow along, but it might be nice. And I had some questions asked about it, so I'm just going to try it out for today, see how it goes. If you want to follow along, go ahead and take out your laptop, follow along. Okay, so click that, and then load the notebook. We're going to run some cells. And I'm going to run that. So here is the data. So there were 2 officials. One was named Blakeman. One was named Prelo. I don't know how to pronounce that. And what they did was during halftime, so they're like, okay, we got to measure these footballs. During halftime, they went into the Patriots locker room and measured a bunch of footballs. So here are 11 of the Patriots footballs. Here is the PSI, the pressure that these footballs were at. Here are the Colts footballs. So they were only able to measure 4 of the Colts footballs before halftime was over. So we have 11 Patriots balls, but only 4 Colts footballs. Okay. So these are our starting data. Please discuss with your partner what else you need to know in order to actually do some analysis on this, or what else you want to know. Okay, so come up with like 5 or 6 questions between you and your partner that you want to find out about this data? Go.
Now, that was the average of the Patriots, an average of the Colts. Average of the Patriots, and average of the Colts, and then a difference. Yeah. Average of 2, right? And then for that, you get all Patriots, all Colts. Yeah.
All right, let me get some questions that you guys had. Any volunteers? Any questions? What else do you need? What else do you want to know about this data, Chase?
Like, what's the NFL standards for how?
Yeah, what are the NFL standards? Great question. Any others? Let's go through like 3 questions. I want 2 more. Yes.
What was the time difference between the measurements?
What was the time difference between the measurements? Okay, valid. Did you have one, Andy?
Sure. How long each of the balls have been in use for?
How long each of the balls? Okay, excellent. So those are 3 questions that we could know, that we could use to get more information about the data. The reason why I'm asking you to do this today is because in real life, you're not going to have me standing up here telling you, okay, here's what we're going to do exactly to this data set. You're just going to get this. And you have to figure out from there what exactly is interesting about this data or what else you need to know in order to actually do your analysis. Okay, so for today, our question is, are the Patriots balls more deflated than the Colts balls? Okay, and to try to answer some of your questions, so basically what happens is at the beginning of the game, okay, both teams like give their balls to the officials check the footballs and they're like, okay, these footballs are within the pressure. And then at this point in the game, so basically they both had their footballs checked. So at the beginning of the game, we can assume that the footballs were like within the standard range. And at halftime, these are the pressures that the footballs are at now. Okay, so we can take a look, and just looking at these numbers here, we see, okay, the Patriots footballs are kind of around like 10, 11, kind of around like 11-ish. The Colts footballs are all like a 12. Okay, so it looks like there is some difference there. What's a way we can use to summarize those differences? We can take a look and try to separate out the Patriots' average pressure and the Colts' average pressure. Maybe that'll help us. Okay, so here we can take football, where let's say ball are the containing Patriots. We only have the Patriots balls. Then we can take the average pressure, and we can take a look at that. I'll leave that as an exercise for you. But basically, when we have some data, our first step is to try to look at it, and then ask some more questions, and then try to do some like initial data manipulation, data analysis to try to see, okay, here's what I think would be useful measures to answer the question that I'm trying to answer. All right. So in this case, we have 2 people who measure the football, so we have different readings, right? So we have Blakeman, and I'm going to call him Agent P. Okay, so Blakeman and Agent P both measure the footballs. We have 2 measurements. Measurements are kind of different here. So for example, like it looks like Agent P's measurements are always a little bit bigger than Blakeman's. But what we can do, and what seems kind of reasonable, is just to take the average. So let's take the average of those 2. So we just get 1 measurement for every football. So we have here football. And I'm going to take a column 1. There is Blakeman's. And here is Agent P's. Here we go. Add them together. Divide by 2. These are the average measurements. So what I'm going to do there is call that averages, and then put that in my football table. So call it averages, football.width column, average at halftime, let's say, and here are the averages. So here are the averages. So all I've done here is create a new column with the average. And so here's another catch. So I got a question which was like, what is the NFL standard for the pressure of these footballs? So the NFL standard is that the footballs need to be between 12.5 psi and 13.5 psi at the beginning of the game. Okay. Now it turns out that it's okay if the footballs are going to deflate a little bit over the course of the game, but at the start of the game they need to be 12.5 to 13.5. And it turned out that when at the start of the game, the footballs, I checked out the Patriots balls and the Colts balls, it looks like the officials were kind of like, okay, both of these teams had like the correct pressure, but the Patriots balls were a little bit more deflated than the Colts balls while still being in like the specific range. So the Patriots balls were around like 12.5 to start off with, and the Colts balls were around 13 to start off with. Okay. So if the balls start at different pressures, we can't just measure the ending pressure at halftime, right? Because if they start off at different pressures, it could have just been the case that since the Patriots balls were a little bit more deflated at the beginning of the game, that they were just more deflated at halftime. So what we want to do instead is measure the drop in initial pressure, right? Because if the Patriots balls started at 12.5 and the Colts balls started at 13, but the Patriots balls were more deflated from the original pressure than the Colts balls were, that gives us a reason to suspect that the Patriots had something going on with their footballs, right? So what I'm going to do now is encode that. So here, oops, the initial pressure for each of these. So what we have here, I believe, let's take a look. Show that. We have 11 Patriots balls and 4 Colts balls. What I'm going to do is I'm going to shorten that. So we have 11 Patriots balls, 4 Colts balls. So what I'm going to do is I'm going to make an array with like 12.5, 12.5, 12.5, 12.5, etc. for 11 times for the Patriots and then 13 for the Colts. So I'm going to take np.ones. So here's a way to create an array of all ones times 12.5. So there's my 12.5s. Oops. Okay. And I'm going to append to that an array of ones. So here's np.append. Here's an array of ones. Similarly, or array of 13, sorry. Times 13. There you go. So here I have 12.5 and 13. So what I'm going to do now is take my football. I'm going to call this temp because we're doing some temporary analysis. Here's my temp table. I'm going to say my temp table equals football or temp.with columns. With column, let's call this initial or estimate at the start of the game and put in my initial pressures there. So there's my temp table. And didn't work. Puzzling. So did I spell that? Oh, right. Don't show. Let's do that. There's my temp. 3 rows. Now I have my temp table, which has the average at the halftime and the estimate at the start of the game. Okay. So the Patriots, it looks like, had an average of 12.5, which is what we're saying. They were at the bottom end of that valid range. And the Colts started out with 13. Okay. So now we can compute the drop in pressure. Let's compute the drop in pressure. So I'm going to take temp.column. Here is 0, 1, 2, 3, 4. Column 4. Subtract out temp.column 3. Subtract out 3. Here are the drops in pressures. And finally, I can add that to my table. Temp.with column drop. And put in that as my drops column. So here are the drops in pressures. These are the things I actually want to compare. I don't want to compare the original starting pressures because the starting pressures for both teams are a little bit different. But I can compare the drops between both teams and take a look at whether the drops look abnormal between the two teams or not. Okay, so save that in my temp table. And finally, I just want to look at the drops. So what I'm going to do is drop equals temp.select out the ball and the drop. Here are just the footballs and how much they dropped. Okay, Now, I don't really care about this Patriots 1, Patriots 2, Patriots 3, whatever, Patriots 11, and then Colts 1, 2, 3, 4. I just want to know which footballs came from the Patriots and which footballs came from the Colts. So what I'm going to do is I'm going to get rid of this number column right here. Okay. And to do that, there are multiple ways of doing it. I could just do with column and just put in an array. So let's call it ball to replace the old one. So if you do with column and the column already exists, this column will replace the old one in my table. So I could just do Patriots a bunch of times. So let's do that, just to show you a simple way of making that work. Patriots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Another thing I could do is take that, put it in a list, and then do times 11. So another nifty shortcut you can do is if you have a list and you multiply it, it turns out that you don't actually get some multiplication of strings. You get just that repeated 11 times. Okay, I can add to it the same thing for the Colts times 4. And now I have an array with 11 Patriots and 4 Colts. There's like a shortcut to creating it. If I don't remember how to do this, I can always just type it by hand. It's not that long, but that's the way to do it. So here I have just Patriots and just Colts. Let's save that. Drops equals drops. Okay, so here I have, let me save that. So here I have Patriots drops and Colts drops. Okay, so usually when you get to this point in your data analysis, you have some numbers, you have some data that you think are directly comparable. Your next step is usually to create a visualization. Try to get a sense of, OK, I have a bunch of numbers here, but what do the numbers look like? Talk over with your partner what visualization you think would work best for trying to see a difference between the Patriots drops and the Colts drops. Go. So what would you want to visualize and why? What would it show? All right, what do you guys think? What visualization can I use? I'd like 2 volunteers. Go ahead. An overlapping histogram. So you're saying put the Patriots on a histogram and then put the Colts on the same one, show them together. Cool, nice. Any other ideas? Sure.
We set a bar chart because basically what you want to know is you just want to have everything on the same scale.
Mm-hmm.
Compare, so we set the right bar chart.
Okay, so bar chart. So the bar chart with 2 categories, Patriots and Colts.
Yeah, I mean, I don't know how I was thinking about it. It's just like repeated for the Patriots.
Oh, I see. So you're saying the Patriots will have 11 bars, the Colts will have. Okay, that's valid as well. In this case, I do think we want to look at a histogram because we have numerical data here. And an overlaying histogram will show us, OK, Patriots have about this distribution. In this case, the Colts have that distribution. When we have numerical data, we usually want to use a histogram to try to see its distribution. Okay, so let's try it out. So here are my drops. I can take. Now, unfortunately, it's a little bit hard to make an overlaying histogram for this particular case because the way that tables work is that to do an overlaying histogram, you need one column with one set of data and another column with another set of data. But unfortunately, we have 11 Patriots measurements, but only 4 Colts measurements. So you won't be able to put that into a table with like 2 columns, one for Patriots and one for Colts, because it turns out that the Colts have less measurements than the Patriots. So that's unfortunate. What I can do instead is I can just plot them both and compare them like one above and one below. So let's try that out. So I want to take out where the team is the Patriots. And I want a histogram, column number 1. Sorry, let's call this ball. You know what? I'm going to name this team. And then drop the ball column. Okay. Or I'll call this ball. You know what? I'll call this ball and then relabel ball with team. There we go. Okay. So there's my drops table. Draw that. Team is Patriots. Okay. So here are my Patriots. I can take the same thing and do it for the Colts. So do it for the Colts. So we see that, but the axes are not the same, right? So these are not super comparable. So let's change it so the axes are the same. So let's do plt.xlim. So this is how you change the limits of the axis. So xlim, let's make them the same. So here I have 0.25-ish, and here I have like 1.9. So I want to do from 0.25 to 1.9. Let's try that. Okay, run that. Okay, so we can see the Patriots balls are kind of around like the 1.0 mark, 1.2 in drops. The Colts are around like 0.5, 0.6. Again, it's not like a super great visualization because these bars are really skinny and these bars are really thick. You can do some more tweaking to adjust the bins to make the thicknesses the same. But I'm just going to leave it at that because I think that shows in this case, like, okay, the Patriots do have a different distribution of drops than the Colts do. Okay, so we notice that we have some difference in the drops. What we want to do is we want to say, okay, is that difference significant? Is it likely to happen by chance if the 2 balls actually had about the same like drop in pressure overall? Okay, so let's run a hypothesis test on this data. So my null hypothesis is that the Patriots and the Colts balls, Colts drops in pressure, came from the same distribution. That is, if a Patriot had a football and a Colt had a football, they started off at different pressures, but overall, the 2 drops in pressure should be roughly the same. Okay, so that would show. So if that were true, then we would say, okay, there's nothing really weird going on with the Patriots balls. It's just they both dropped in pressure and they just started off at different pressures. On the other hand, my alternative would be the 2 teams drops in pressure and not come from the same distribution. But there's something weird going on. The drops and pressures for the 2 teams are not the same. So these are the 2 hypotheses I want to test out. Okay. So I've stated my null, I've stated my alternative. My next step is to choose a test statistic I can use to measure how far away I am from the null. Okay. Talk over with your partner what a good test statistic for this case would be. Go ahead. And here, for reference, is a drop table. So we have this table. I want to find a good statistic I can use for this hypothesis test.
You have an average drop for Patriots and an average drop for Colts. Difference between the 2 drops. See how far apart they are. See if this combination here is likely to.
Okay, so I've heard a couple people mention like average drop, average difference in drops. And yeah, so we can try that. So let's try it out. So what we want to do is take this table and say, OK, if the Patriots had like a lot, if the Patriots drops are really big and the Colts drops are really small, I want to say, OK, that seems pretty unlikely to occur. So I want some measure of that. And so the average drop seems like a good candidate. To do the average drop, what we want to do is we want to take the average of the Patriot and the average of the Colts, which we can accomplish with a group. So group by the team, and use np.average to average out the measurements for each team. We can see that indeed the Colts had about 0.5 psi drop, and the Patriots had a 1.2 psi drop, which is pretty big. But we don't really have a sense of what is like big enough to make a judgment call. What I'm going to do now is just I'm going to take these two numbers and subtract them from each other. So take the group and take that column. So here are the two drops. Okay, and I'm going to save that into my averages, into an array called averages. Then I'm going to take averages.item 0, subtract it from averages.item 1. So now I have some measurement. Now, in this case, our alternative is that the two drops in pressures did not come from the same distribution, right? So it could have been that the Colts had a bigger drop or the Patriots had a bigger drop. We're just trying to measure whether or not they came from the same place, whether or not the drops are equal. Our alternative is that the drops in pressures were not really equal, right? So in this case, we do want to take the absolute value because we want to measure, OK, even if one was bigger than the other, I want to say, OK, there was a difference, whether or not like the Colts had a bigger drop or the Patriots did. Okay, so that's my alternative. Because of that, I'll choose the absolute difference of mean pressure like measurements. Okay, so that is my test statistic. I'm going to put that into a function. So define difference in averages, average drop, and I'll call it with a table and use a table here instead of drops. So then I can do difference in average drop with drops. And I forgot to return. Return, there we go. So that's our measurement of difference in average drop. Okay, cool. So now that we've chosen a test statistic, our next step is to simulate, right? So you want to say, OK, assume the null is true, simulate a bunch of random samples, find the distribution of this difference in the absolute difference in average drop, and see whether my average drop, so this is my observed test statistic, see if that observed value is likely to occur by chance. So talk over with your neighbor now how you would simulate drawing more samples, assuming that the null is true. Try it out. It's a tricky question.
Sample from that table.
So talk about it, and I'm going to take attendance. OK, so quick note. We changed the attendance link. The old attendance form had some issues where it looked like sometimes when you filled it out, Google Forms would mysteriously just make your emails vanish. So we're working out something to work out attendance for that. We're thinking something like if we record you down for attendance at least once in a week, you'll get attendance for that week. But in the meantime, we made a new form. Hopefully the new form will work better. The new link is bit.ly/@-d. I was like, OK, I need something that's kind of similar to @d8, but not @d8, so I chose @-d. It's shorter, so I'm going to open it up, try it out now. So there we go. I'm very dissatisfied.
Can we go back to the link?
Yes. bit.ly/@-d. When you're done, talk over with your partner how you would simulate drawing more samples, assuming that the null is true. So again, our null hypothesis is the two samples came from the same distribution. And what we want to do is we want to assume that's true, draw more samples. Talk it over.
So we have to deal with like 15 drops for each of the 15 balls. We can like randomly sample 15 times table, maybe 5,000 times. Combinations of those 15. average shots and look at the test statistic. And then from that, we can find our p-value, saying what is the percentage portion greater than that test statistic. So how likely are they to be from the same distribution? Does that make sense? Yeah, I was gonna say like drops dot sample 15 is like, or dot sample numbers. Yeah, to sample 15 of them at a time.
Okay, go ahead and discuss.
Yeah.
I'm just going to wait here until I see people talking about it.
I mean, what is 15 factorial? We have a calculator for that. Python calculator, let's do 15 factorial. Or I don't know how do you do factorial on Python?
You can Google it.
Okay.
Yeah, that just
Yeah, so like hello. Factorial 15. So we can take a lot of samples from this. Is how many samples we can get from that table. And we only need like 1,000.
All right, so I see a lot of puzzled expressions. That is to be expected because I haven't talked about how to do it. And that's the topic of today's lecture, basically. But if you've tried, so you look at this and you're like, OK, assuming that is true and take a sample, unfortunately, it's not as easy as we've done before. Because, for example, before, let's say we're trying to decide whether a coin is fair or not, right? In that case, we can say, OK, my null is that the coin is fair. So I have half a chance of heads, half a chance of tails. I can just flip a coin randomly using my computer to simulate that. We're just saying, OK, the two drops in pressures between the two teams are about the same, right? But we don't know what that is. We don't know exactly what that number is. And so it becomes difficult to actually specify exactly how to sample in order to get something that looks like a random sample from a population. So it's not as easy as that. Our method for doing it, okay, so I'm going to close this. Is anyone still taking attendance? All right, closing it. I don't like that it drops my emails. All right, get out of my face. OK, great. Close it. Cool. OK, so when we have two samples, we have to have some method of comparing the two samples. In our case, we want to see, OK, do our two samples look different or not? All right. And the little trick that we're going to do is what's called a permutation test. OK, so what we're going to do is we're going to say, OK, if the Patriots balls and the Colts balls came from the same distribution, as in the drops look roughly the same, have about the same average, have about the same variation, then it shouldn't matter. So let's say these are the Patriots drops and these are the Colts drops. It shouldn't matter whether they're in this order or whether they're in this order, right? So the idea is, OK, if my two samples really did come from the same distribution, then if I shuffle the readings between the two samples, I should still end up with something that looks pretty much the same, right? If they actually did come to the same place, shuffling should leave them about the same. So that's the idea. So we're going to say, OK, shuffle the drops between the two samples. And that's another sample under the null hypothesis that the drops came from the same distribution. Okay. So the basic idea is, call this permutation test. So we're testing whether the two samples are drawn randomly from the same underlying distribution. Okay. The key idea is if the null hypothesis is true, then any rearrangement of my data between the two samples is equally likely, right? So because of that, we're going to shuffle it, compute my observed, shuffle it again, compute my observed, and use that to create a distribution of my test statistic under the null hypothesis. All right. So cool idea. Let's see if it actually works. So here I have my drops table. What I'm going to do is take a sample. So by default, dot sample will take a sample equal to the number of rows in my original table, and it will take it with replacement, so I want it without replacement. Equals false. And I try that, and I just get team and drop shuffled. What's the problem here? The problem is that I want to shuffle the drops and then assign them back to the teams. If I sample here and do a shuffling this way, I just like move the rows around in my table, but I'm not actually doing anything different with my test statistic. Okay? So in this case, if I actually were to take the difference in average drop and put that in there, I'll get the exact same thing because I'm just shuffling around like the Patriots and the Colts along with the drops. I want to take my drops, shuffle them, and then reassign them back to Patriots and Colts to actually shuffle around that drops column. Okay, so here's what I want to do. I want to take this column right here and just shuffle around the numbers, but keep these teams here the same. So to do that, I'm going to select out my drop column first. So if I select out my drop column, now I just have the numbers without them being to a team. Then I can sample with replacement false. That gives me a shuffling of the drops. Okay. So I'm going to call this shuffled. So here's another shuffling of drops. What I can do there is take the drops table, take the team column out of the drops table, and then say, OK, take this column here and stick it back in my original table. So I'm going to take the team. So here is just the teams. Here I have just the drops. I'm going to put the teams, take the drops, put them together, team drops. OK, so with column drop, and put in this here. This is a table, so I need to grab out the first column in order to actually have it be an array. So now I have a table with the drop shuffle. If I run this again, shuffle drops. Okay, excellent. So here I'm going to call this my sample. My sample. What I can do now is visualize what happened in my sample. So I can go back up here, take these two histograms. Let's take both of them, copy. Let's see if this works. Sample, excellent. Take my drops, take my sample, replace it with my sample. And what we should see is here is a Patriots distribution of drops in my new sample. Here is a Colts distribution. Indeed, because we shuffle the drops around, the two distributions look roughly the same. Okay, so we have here Patriots drops, Colts drops in my new sample with the shuffle drops. All right, so now all I have to do is repeat this. So let's take that, take my sample. Conveniently enough, we already have a method for doing that. We have the test statistic function, difference in average drop. So if I call that on my sample, in this case, I get 0.11. Okay. What I can do is I want to run that over and over. So let me group the code together. So I'm going to take this, which draws a new sample, draw a new sample, take the average drop, do that. Here's almost 0. Here's like 1.12, 0.05. Okay, so I'm running this cell over and over again. I can just do a for loop to automate that. Okay, so here I'm going to do repetitions. Repetitions equals, let's do 10,000. For I in mp.a range, repetitions. Paste that in there, indent that. Okay. But now I'm computing 10,000 of these test statistics. As usual, I'm going to make an array. So I'm going to say, call this, let's see, sampled stats equals make array into that array. So sampled stats equals sample stats dot np.append, sorry, sample stats with my difference in average drop. Now I can take a look at my sample stats. Bam. And these are 10,000 simulations of my test statistic. The average drop in pressure, the absolute value of the average drop in pressure across the two teams. Here are all my values. Okay. What I'm going to do now is put them into a table. Let's call this the null. So here I have the table. We're getting so close. With column null distribution. Put my sampled stats in there. I have a table containing these sample test statistics. Let's draw a histogram. Null.hist. And here we go. Okay. So we can see here that under the null hypothesis that both teams' drops came from the same place, most of the values are very close to 0, which makes sense, right? The null hypothesis says the difference in drops between the two teams should be about the same. There's nothing special. There's no difference between the two teams. And we see here that the distribution of my statistic matches that. Right? So deshuffling does give us a distribution that is close to 0. I can take now our observed value. So what I'm going to do now is take the observed value. I have here a nifty function that breaks, unfortunately. Oops. We have here the observed value. Let me fix that. Of, let's see, what was it called? Difference in average drop of my drops table. This is my original observed test statistic. So it's like over here at 0.73. Just to visualize what's going on here, I can run that. Here's my first sample. Here's a line with my test statistic. I take my samples, take my samples, take my samples. And we can see a distribution becoming more and more smooth. And I can scroll up to here, and the distribution is like pretty smooth, and then I can keep going. And there's my final null distribution, the estimation of my test statistic. Okay. Any questions about that? Yeah, Kevin?
So on the table, we're basically taking different possible permutations of those 15 drops in pressure.
That's right. So the key idea is, if the null were actually true, shuffling doesn't really do anything special because the two samples came from the same place. If the two came from the same place and shuffling doesn't do anything special, then I can just shuffle at will and get a measurement of how variable my test statistic is. So that, in a sense, so shuffling there is equivalent to taking a sample from my original population in that case. We're using that instead of going back to our original population. Cool. So all we have to do left is calculate a p-value. That's not too hard. I take my sampled stats, grab that. Here are the numbers. Okay. I want to figure out how many of those are greater than or equal to my observed. I can find a proportion by doing np.count non-zero. At 41 out of 10,000. My p-value is 0.0041. Okay. So by any like reasonable p-value, this is statistically significant. What we're saying here is, okay, it looks like there is some difference in the drops and pressures between Patriots and Colts. So it does seem fishy. And in fact, they found it to be fishy as well. So the official analysis was the average pressure drop of Patriots game balls exceeded the average pressure drop by 0.45 to 1.02 psi, blah, 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 assuming the initial pressure of 12.5 for the Patriots and 13 for the Colts. So what they found was that, there is some difference between the Patriots drops and the Colts drops. If you look at this, you see, they actually calculated a range of numbers, like a range of what they think is like valid drops in the pressures in the game balls. We'll talk about how to do that later on this week. Our test, on the other hand, can only conclude that there is some difference between the two teams. Okay? It does not say how big that difference is. In fact, our test, as the way we created it, doesn't even say whether the Patriots dropped more or the Colts dropped more in terms of like the pressures, right? So our test is pretty limited in what it can say, and that's because of the way that we've constructed our null alternative hypotheses. Oftentimes, it is nicer to get a range like this. And we'll be talking about how to do that in just a couple of days. Okay? But the people investigating this ball case went in, took a look, and they used the statistical analysis along with like text messages that the players sent to each other, along with all sorts of things. And basically, they said, OK, there seems like there's something going on. You should probably find Tom Brady like $1 million. And so they find Tom Brady $1 million. Cool. Any questions? OK, so just to recap, that was supposed to come out one at a time. But before we were looking at one sample, right? So enemy warplanes, we had one sample of planes. Rolling a die, we had like one set of dice rolls. We had a lot of methods for looking at different ways of looking. We had a lot of different methods for looking at one sample before. That's all that we've covered so far in this class. Today, I introduced a method for working with two samples and comparing to see whether there's a difference between the two. It's really convenient, and it turns out that in practice, like we do want to look at two samples pretty often, because, for example, if we're testing in medicine, we want to see, OK, was my treatment better than my control, or did something else happen, right? A lot of times we have two groups and we want to compare. In this case, our typical null hypothesis is that the two samples came from the same distribution. The values are roughly the same. If that is our null hypothesis, we can use a permutation test to get more samples, assuming that the null is true. Instead of going back and getting more samples, we can use a permutation test to simulate drawing more, just like how we simulated doing the coin flip. So here's one more method of doing simulation that you guys should keep in your tool belt. With that method, you can calculate the p-value as usual. Hooray, I'll see you tomorrow.